In this video, we're going to look at the adiabatic expansion or compression of an ideal gas. Adiabatic means that there is no heat transfer into or out of the system throughout the process, right? So this means that we would need to be doing this process in a very insulated environment, right? So if we imagine that we have some piston where we could compress or expand the gas, that piston would have to be surrounded by some kind of an insulating material such that no heat can get in or out of the gas. Of course, this is an idealization. We can never actually make something fully adiabatic because it will always have some amount of heat transfer into or out of the system. But we can get things close to adiabatic. And in general, we can think of things as being adiabatic if they happen very quickly in comparison to the amount of time that it takes for a system to come into thermal equilibrium. So, for example, if you imagine putting this gas inside of a thermos, and then we compress the gas very quickly over fractions of a second, right? The thermos isn't going to be heating or cooling the gas itself by any significant amount over that fraction of a second. So that process can be considered very close to adiabatic because it happens much faster than the amount of time it takes for a significant amount of heat to flow, right? If you think about a gas inside of a thermos, you would think that it would take at least minutes, if not much longer, for that gas to come into thermal equilibrium with its surroundings, right? So I could put a very cold gas inside of a thermos, and it would take longer than fractions of a second for it to come into thermal equilibrium. That kind of gives us a sense of the time it takes for heat to transfer, a significant amount of heat to transfer into the gas. And if we do our process much, much faster than that, it will be approximately adiabatic, and we can use this approximation. Okay, so adiabatic, when we write down our change in energy for the gas, then our Q, our heat, is 0. So our change in energy is only the change in energy of the gas due to the work that we do on the gas, right? So we have delta U equals work, which is always equal to the negative of the integral P dV. Okay, but now we're actually going to do a little bit of a trick. So what we're going to do is we're going to think about not a large change in energy, but an infinitesimal change in energy of the gas due to an infinitesimal change in volume. So instead of taking the integral, we're just going to write down, okay, a little change in the gas, the energy of the gas, is equal to P dV, a little change in volume, right? And as we can see here, if we want a change in the energy over some macroscopic motion, we can say delta U equals the integral of this du, which is then equal to integral of P dV, right? So we're basically taking this and kind of unintegrating both sides to just consider an infinitesimal amount. And the reason that it's nice to do this is because we can actually change variables from U to T, from energy to temperature, by knowing that this gas obeys the equipartition theorem, right? The equipartition theorem says that the energy of a substance, it doesn't have to be an ideal gas, but it can be, that stores energy only in quadratic forms of energy, like kinetic energy, which goes like V squared, or spring energy, which goes like position squared, follows this formula, where the energy is equal to the number of degrees of freedom, how many different ways can it store that energy, multiplied by nkt divided by 2. So our ideal gas follows the equipartition theorem, which means that energy is directly proportional to temperature. Everything else on the right side here is a constant. F is a constant for a given gas, right? So we'd have to know what, say for example, a diatomic molecule would have 5 degrees of freedom, so F would be 5 for that, for a gas made of that molecule. Okay, then we can take du dt and find du in terms of dt. So we are able to change our integration variable here from du to dt, right? So all I did was say du is equal to f over 2 nk dt. So now we have a relationship between an integral in terms of temperature and an integral in terms of volume. And both of these, because delta U is equal to work, are equal to the change in energy of the system and the work that is done on the system, right? Those two are the same quantity for an adiabatic process. Okay, so now what we can do is we can think about, well, if we want to calculate the work that is done on the gas, we have two options for doing that. If we are given the initial and final temperature, we can take an integral over dt. If we are given the initial and final volume, we can take an integral over dv. Okay, first with the temperature. So taking this integral is obviously we just end up with a t. Applying our limits of integration, we get f over 2 nk t final minus t initial. And so our change in energy just looks like our change in temperature multiplied by a constant, which is exactly what you would guess from looking at this equation anyway. So calculating the work done in compressing or expanding an ideal gas, if you know the initial and final temperatures, you can just use this. Okay, the other case is if we know the initial and final volume, then we need to be able to figure out a way to write pressure in terms of constants and volume. And the expression that we're going to use is that P times V to the gamma, where gamma is a function of the number of degrees of freedom. This expression is derived in Schroeder on page 25 and 26, so you can go there and see where this expression comes from. But for right now, we're just going to use it. And so this nicely gives us a relationship between the pressure and volume at any time and the pressure and volume, say, at the initial time. So if I know the initial pressure and the initial volume, I can find out what this constant is, and I can set the pressure and volume at any time equal to that constant, right? And this gives us a perfect way of writing the pressure in terms of volume. So that is to say that we can write the work as P initial, V initial, right, divided by V raised to the gamma. That is this expression solved for the pressure. And then we can take that integral and find out what the work done is. So either of these integrals will work in order to find the change in energy or the work done on the gas. And it just depends on which variables you have in your problem as to which of these integrals you want to do. Now let's try a specific example of finding the work done in expanding an ideal gas adiabatically. So our setup is that we have a monatomic ideal gas. Monatomic is a key word. It tells you that the degrees of freedom is only 3. Monatomic gases, meaning they have only one atom. The spin of these atoms does not contribute an energy that we count towards the energy of the gas, which means that the only energy types that a monatomic ideal gas has is translational energy, energy of their motion. And since there are 3 directions that they can move in, X, Y, and Z, there are 3 degrees of freedom for this. So when you see monatomic, you should think that the number of degrees of freedom is 3. Okay, this monatomic ideal gas is initially at atmospheric pressure, which is 101 times 10 to the 3 pascals, and 300 Kelvin. It is expanded adiabatically until the temperature is 280 Kelvin. So its temperature is dropping. And the gas has an initial volume of 10 to the 3rd cubic meters. And we want to find delta U. So we're actually going to solve this problem in two different ways. We're going to solve it using temperature because that seems like the most obvious answer since we're given T initial and T final. And then we're also going to solve it using the volume integral, negative integral P dV, and we're going to see that those two give us the same result. Okay, so our change in energy of the gas is equal to the work done on the gas, which is given by this, as we just found. And the only thing that we're kind of missing here is that N is not something that's given in the problem. But we can solve that using the ideal gas law. So we know NKT initial equals P initial V initial. We know pressure initial, volume initial, and initial temperature, which means that we can solve for NK in terms of quantities that we do know. And this ends up being this value here. When we plug in that value for NK and F equals 3, with our delta T being negative 20 Kelvin, because we started at 300 Kelvin and we ended at 280, so we lost 20 Kelvin, we get negative 101 times 10 to the 3 joules. So we can see that the change in energy of the gas is negative. This indicates that the gas is losing energy, right? Because delta U, the change in energy of the gas, is negative. The gas is losing energy. And there's two basic ways of thinking about this. One, we can think about the work done on the gas. This is what our W represents, how much work was done on the gas. Well, the force that is being applied to the gas by the piston points to the left, but the displacement of the piston is to the right. So the work done by the external piston is negative, right? Because the displacement is in the opposite direction of the force, right? So the piston is doing negative work on the gas. It is taking energy out of the gas system. That's why our work is negative, and that's why our delta U, the energy of the gas, is negative. A separate way to think about this is to think about the work done by the gas. So the work done by the gas is equal to the negative of the work done on the gas. Work done by the gas is equal to the negative of the work done on the gas. So the work done on the gas is negative, so the work done by the gas is positive. The gas is doing positive work as it pushes the piston outward. Where does the energy for that work, that positive work that the gas is doing, come from? It must come from the gas itself, right? So if the gas wants to do positive work in pushing the piston outward, it must lose its energy. How much energy? Well, exactly this amount of energy, right? So I think it's slightly more intuitive to think in this case about, is the gas itself doing positive or negative work? If the gas is pushing outward on the cylinder, it is doing positive work, which means it must be losing energy. So this delta U must be negative. Now let's solve this same problem, except we'll use the other integral. We'll use the integral of P dV in order to find the change in energy and the work. So the same setup, our F, our number of degrees of freedom, is still equal to 3. And we have two relations here that we are going to have to use. Both of these can be found in Schroeder on page 25 and 26, the derivation of them. Okay, so we know that PV to the gamma, where gamma is this function of the number of degrees of freedom, is equal to a constant. And we know that V times T to the F over 2 is equal to a constant. So the integral that we would like to do is the integral of P dV, but we don't know the limits of this integral. We know V initial because we're told it, but we don't know V final right away. So the first thing that we do is we need to figure out what volume, what final volume are we going to integrate to, And to do that, we use our relationship with temperature and volume, because we know the initial temperature and we know the final temperature. So we can find the final volume using this relationship here, where we've just set the final volume times T to the F over 2 equal to the initial volume times T initial to the F over 2. And we get this as our final volume. So now we have the limits of our integral. We have V initial and we have V final. And we set up our integral with using this relationship here, where pressure looks like the initial pressure times the initial volume raised to the gamma divided by the volume at any given time at our final time to the 5/3. Okay, and taking this integral, we end up with this expression here. Plugging in the limits of integration, we end up with exactly the same answer as we got in the temperature integral. So it doesn't actually matter which of these integrals you decide to use. Mostly it's based on what kind of information you have, though you'll always have enough information to go back and forth between the two.